Digestate treatment and resource recovery. In this segment, we are going to discuss about different treatment and enhancement options for digestate, as well as different resource recovery options from digestate. The nutrient-rich byproduct of anaerobic digestion process is known as digestate. Digestate usually contains all the nitrogen, phosphorus, and potassium present in the original feedstocks. It has been used as fertilizer and soil conditioner historically. But currently, other usages of digestate are also being investigated. But ultimately, the digestate treatment and resource recovery option will depend on the overall plant economy and profits generated from the final products. So before adopting any recovery option or treatment train, the following points need to be considered. Is the chosen treatment train or recovery route most economically viable one, considering market demand, production cost, and rate of return? What is the state of the chosen technology, and what is the level of risk associated with its performance? Does the end product or recovered product and its final usage meet all the local regulatory compliance and requirements? So if the answers come favorable for all these questions, then only one should proceed with the chosen technology. Let's start with digestate treatment and enhancement options. Digestate contains some essential plant nutrients such as phosphorus, nitrogen, potassium, and sulfur. However, they may also contain contaminants such as heavy metals, toxic chemicals, pharmaceuticals, infectious microorganisms, etc. depending on the feedstock used. Digestate treatment should be chosen based on its physical, chemical, and biological properties, as well as desired in-use or disposal options. The current and evolving digestate treatment and enhancement option can be categorized in the following 5 categories. That is physical, thermal, conversion, biological, and chemical treatment and enhancement options. So let's discuss them one by one. Physical treatment and enhancement options. In a wet anaerobic digestion process, digestate is basically in a liquid state with around 4 to 10% of solids. To convert this digestate as a valuable fertilizer, nutrients need to be concentrated, or in other words, water in the digestate needs to be reduced. This is usually done through various separation technologies like thickening, dewatering, filtering, etc. that separate the fiber or solid part of the digestate from the liquid part. The separated liquid part can also be used as processed water or recycled water after receiving further treatment. Several separation technologies are discussed in the following slides. Thickening. Thickening is generally accomplished by gravity separation and physical processes like gravity settling, flotation, centrifugation, gravity belt thickener, and rotary drum thickener technology. Sometimes different coagulants are also added to increase solid capture and process efficiency. This is a partial solid-liquid separation process, and the final liquid has usually 5 to 10% solids based on the technology adopted. Dewatering. Dewatering is applied when a higher percentage of solids are desired in the final separated product. Generally, dewatering technology can achieve greater than 20% of solids in the separated cake of this digestate. The commonly used dewatering technologies are solid ball centrifuges, weld filter presses, recessed filter presses, etc. The selection technology is usually decided based on the characteristics of the digestate, the desired characteristics of the dewatered products, as well as the economy and space available in the treatment plant. Different coagulants are also added during the dewatering process to improve solid capture and operability of the process. The liquid generated from the dewatering process contain high amount of ammonia and potassium and required further treatment prior to disposal. Membrane filtration. Membrane acts as a physical barrier or molecular sieve and allows the water to pass through while retaining the solids. Different types of membrane products and technologies are available as a separation tool, like microfiltration, ultrafiltration, and reverse osmosis. But due to their small pore sizes, membranes are very susceptible to fouling and they are usually used to treat the separated liquid from the digestate to purify them further. So rather than treating the solid part of the digestate, they are better suitable to treat the liquid portion of the digestate. And high quality product water suitable for use can be achieved through this membrane separation. The concentrate from membrane separation process can be used as fertilizer. Thermal treatment and enhancement options. In thermal treatment, thermal energy or heat is being used to dry up the digestate. This can be achieved by using various types of drying and evaporating technologies, such as conventional sand drying bed, paved drying bed, artificial media drying beds, vacuum-assisted drying beds, solar drying beds, rotary sludge dryer, fluidized bed dryer, and evaporator. Thermally dried product has a great reduced water content and volume. As a result, it is very convenient for handling, storing, and tracking. The dried product can be pelletized, and that further facilitate storage, transportation, and use as a fertilizer. Conversion treatment and enhancement options. In the conversion treatment, digestate is converted or break down into different end products that can be used in alternative application rather than conventional land-based one. Most of the conversion technologies require dewatered sludge with low moisture content and preferably in a pelletized form. Some of the conversion technologies are discussed in the coming slides. Incineration. In incineration, digestate is totally converted to oxidized end product, mainly carbon dioxide, water, and ash. The ash generated in the process can be used as a construction material for road or concrete. Phosphorus can also be recovered from ash by acid leaching technology. The advantages of incineration are maximum volume reduction, pathogen and toxin compound destruction, as well as resource recovery potential. But the high capital and operating cost, adverse environmental effects associated with the process emission, and potential hazard of the generated residual make it a less preferable technology. Gasification. In gasification process, partial combustion of organic matter is conducted to produce an end product called syngas or synthesis gas. Syngas is mainly a mixture of carbon monoxide and hydrogen, and it can be used to produce energy. The process prefers a dry pelletized form and low moisture content in the feed. Water oxidation. In the water oxidation process, digestate is oxidized within the liquid phase rather than the gaseous phase, in contrast to the other conversion processes. This process is achieved at elevated temperatures and high pressure to prevent evaporation. The end products are a mineral sludge, a liquid effluent, and off gases. There are usually no pretreatment required for this process. Let's move to biological treatment and enhancement options. In biological treatments, microbial species are used for reducing organic content as well as for producing useful end products like fertilizer and biofuel. So some of them are discussed as follows. Reed beds. Reed bed is a passive composting system that dewaters and stabilizes the digestate over a long period of time. Typically, the whole digestate is fed into the bed of reeds and then it gets treated by the microorganism at the root of the plants. The water gets removed over time via collection basin and evapotranspiration. Reed bed is similar in appearance of a subsurface flow constructed wetland. Composting. Composting utilizes a variety of microbial communities including bacteria, actinomycetes, and fungi to stabilize the digestate. In composting, around 20 to 30% of solids are converted to carbon dioxide and water. Composting can be accomplished both aerobically and anaerobically, although partial aerobic condition is the most common one in practice. Sometimes amendments material like sawdust, straw are added with the feed to aid aeration and reduce mixture weight and moisture content. Moreover, adding a bulking agent is also common to provide structural support and to increase porosity of the mix. The most commonly used bulking agents are wood chips. Some design considerations for aerobic sludge composting are as follows. The initial CN ratio should be in the range of 20:1 to 35:1 by weight. The volatile solid of the mix should be greater than 30% of the total solids. pH of the mixture should be in the range of 6 to 9, and the temperature should be in the range of 50 to 60 degrees centigrade for optimum result. Currently, different types of composting methods are in practice, such as aerated static tile, windrow, or in-vessel composting systems. At the end, composting operation and its subsequent use should be matched with the local regulation to ensure public health and environmental safety. Biological oxidation. Biological oxidations are various biological wastewater treatment processes that can employ to treat either the whole digestate or the liquid portion of the digestate. Process selection depends on both the digestate solid content as well as solid tolerance capability of the process. Some of such biological treatment processes are sequencing batch reactors, membrane bioreactors, etc. These processes use bacterial population that oxidized BOD and ammonia in the presence of oxygen. The effluent resulted from this process are very high in quality and can be reused. The biological biomass can be returned to the digester. Biofuel production. Digestate has the potential to be used as feedstock for biofuel production. The liquid part of the digestate can be used to grow algal population and produce algae that later can be used for biofuel production. Lipids from algae can be separated and converted into biofuel, and the remaining algal biomass can either be sent back to the digester or sold as animal feed. The separated water from algal population can be used as process water or other irrigation purposes. And several such techniques are currently being developed. Struvite production. Phosphorus and ammonia can be recovered from the digestate or its centrate in the form of struvite, a solid compound made of magnesium, ammonium, and phosphate. Struvite can be used as a fertilizer, and because of its slow release property, it stays in the soil longer rather than washed off by the water. The struvite precipitation is usually carried out in a fluidized bed type of reactor. The reaction is highly pH dependent, with optimum pH value being at around pH 10. Usually magnesium is added to the process and pH is artificially elevated to create the optimum environment. pH can be increased by dosing with sodium or magnesium hydroxide, and magnesium ion concentration can be increased by adding magnesium hydroxide or chloride. But adding magnesium hydroxide is advantageous because it increases both pH and magnesium ion in the solution. Struvite contains equivalent amounts of ammonia and phosphate, and digestate usually contain more ammonium than phosphate. So the resulting effluent may require more treatment to recover or remove ammonia before disposal. Ostara, a Canadian nutrient recovery company, has developed a struvite production technology known as Pearl Nutrient Recovery Process that has several full-scale installations in Canada and USA. This technology is based on controlled chemical precipitation in a fluidized bed reactor that recovers struvite in the crystallized form. The resulting product is marketed as a commercial fertilizer called Crystal Green. Ammonia stripping. Usually ammonia stripping is conducted in a packed column tower. Ammonia reacts with water to form ammonium hydroxide. In ammonia stripping of digestate centrate, pH of the solution is increased until it reaches to 10.8 to 11.5. At increased temperature and pH, ammonium hydroxide converts to ammonia gas. The air or steam is passed through the tower in a counterflow pattern to absorb the ammonia. This stripping gas is then passed through an acid scrubbing tower, operating with either sulfuric or nitric acid. The ammonia comes out of the scrubber as ammonium sulfate or nitrate based on the acid used for scrubbing. The process air or steam can be reused. Ammonia can also be recovered via ion exchange process where digestate is fed into a packed bed of absorbent like zeolites, clays, or resins. Their ammonium gets selectively absorbed by ion exchange. Once saturated, the column is taken offline and regenerated, recovering the ammonium. Alkaline stabilization. Alkaline stabilization is a method of eliminating Reisson's condition of digestate using alkaline material like lime. In lime stabilization process, the pH of the digestate is raised to 12 or higher to create an environment that halts or slows down further microbial reaction. As a result, the digestate will not putrefy, create odor, or create a health hazard as long as the high pH condition remains. This process can also inactivate microorganisms and pathogens present in the digestate. Resource recovery from digestate. Biosolids and digestate have long been used to agricultural lands to take advantage of the nutrients and macronutrients of these products, with the aim to increase soil fertility or structure. But there are also some disadvantages associated with the land application, such as high nitrogen content with potential of ammonia and nitrate pollution, high dilution requirements, needs for supplementary nutrient addition to create a balanced fertilizing feed, etc. But recently, a wide range of resource recovery options has evolved from the digestate beyond this conventional agricultural use. Some of the drivers behind this evolution are mainly search for renewable fuel sources, reducing greenhouse gases, and reducing transportation costs to the suitable application sites. At present, the focus is on complete nutrient recovery and creating value-added products from digestate. In recent practice, digestate is separated in two different fractions, fiber and liquid. These fractions have different nutrient profile with different potential uses and potential markets. And we're going to discuss them in the coming slides. So in this slide, we have separated digestate and its solid fiber, and we have shown different treatment and enhancement technology and the beneficial end use of the final products. So we can see that digestate can be taken as a whole, and after drying it can apply to land. And also we can treat digestate in reed beds, and the water can be used, or the remaining can be used as land application. We can take digestate, and after dewatering we can get the solid fiber, and the solid fiber after alkaline stabilization can be used as soil amendments. And after composting, it can be used as after certain nutrient addition, after producing balanced fertilizer, we can use it to land as well. And after taking the solid fiber and after further drying it and produce pelletized form, we can use it in gasification to produce syngas, in pyrolysis to produce char for soil amendments, and in incineration, and the end product is ash that can be used as construction materials. In this slide, we have the liquid portion of the digestate after dewatering. This liquid portion can further be treated in wastewater treatment plants like NBR, SBR, and we can have reusable water that can be used for process water, irrigation water, etc. We can use that liquid portion for algal production, and we can produce biofuel. And after evaporating the liquid portion, we can have concentrated fertilizer. We also can use this liquid portion to produce struvite, and we can recover nutrient, and also after ammonia stripping we can recover valuable nutrient. At the end note, with various evolving resource recovery technologies from digestate, before selecting any treatment or recovery technology, the overall plant economy should also be kept in mind, and the use of the final products and their existing market should also be considered. So with this slide, I am going to close this segment of digestate treatment and resource recovery, and we'll move to our last lesson, that is the economy of anaerobic digester, and we'll continue from there.